Welcome to lesson 42. We're going to add some vectors together. So first, let's recall what we were doing last time. First of all, we explained what a vector is. So this arrow here is an example of a vector. If you want to refer to the vector as a whole, you might call it V. You got to call it something, so you might call it V. And then remember this special arrow on top tells you it's a vector. And what's a vector? Well, a vector is, you can think of it as an arrow, but what it basically has is it has two parts to it. A magnitude, it's this big, it's this long, we call that R, but it also has a direction, it's going that way, which we might measure from the x-axis, this angle here. Remember, that's called standard position. When you measure from the x-axis, it's called standard position. So anyway, we were playing with that last time, and we saw that, like, for example, you can think of this vector, V, as having two parts to it. It has a little bit of a upward and a little bit of a leftward to it. I mean, you can think of it by looking over here and saying, yeah, if I drop a plumb bob to the x-axis, you might say I've got this much action going east, going along the x-axis. And is there such a thing as a sideways plumb bob? Well, whatever. If you do that, you can say, oh, look, it's got a certain y action to it too. So you could have like an airplane flying 100 miles an hour this way, and this looks like a pretty stiff cross breeze, but whatever. Let's say there's a 50-mile-an-hour cross breeze, and what are you actually going to see? You're going to see the airplane pointing this way, and it's going to always be pointing this way because that's the way the engine's trying to make it go, right? Go that way, go that way, go that way, go that way by 100 miles an hour. That's the x component. But it's going to sort of be drifting as it goes. And this is the y component. That's the drifting component, if you will. And so the actual speed of the plane, if you're up above in a mothership looking down, you see the plane going this way. It's like, yeah, he's pointed this way, but you see him going that way. And maybe you've seen an airplane go by on a windy day and you've noticed this effect. The plane is pointed one way, but there's definitely a drift to it. So its net speed, its total speed, its actual speed relative to the Earth is actually along a diagonal path. It's actually going that way, right? If you're aiming straight for Paris, you're not going to get to Paris. You're going to get to London or whatever. So anyway, that's the idea of vectors. Then we had these nice formulas here, right? Here's how you can, if you know what the, trying to erase all this. Okay, if you know what the x and y components are, then you can put them together to find out how long this vector is, because basically it's a Pythagorean theorem, right? So remember, this is Vy, so this is the same size, right? That's Vy. So you can see there's a nice little right triangle here begging you to use the Pythagorean theorem. And so that's how you can get the length of the vector. If this is the angle theta, you can do a SOHCAHTOA. You end up, when all is said and done, doing a shift tangent of the y over the x. Remember, if this is theta over here, this is your tangent action, right? Tangent of theta would be Vy over Vx. So theta would be the shift tangent of Vy over Vx. So you got those two formulas. And then you've got, if you want to go the other way, you've got these two formulas. So you know what the r is, you know what the theta is. Question, how big is this component? And again, this falls out of SOHCAHTOA, basically. You can tell there's a cosine involved, right? The cosine of theta would be the x component over the r. And if you just basically rearrange that, you get this. And similarly, you can do SOHCAHTOA with a sine to get the y component. Okay, so that's where these come from. So that's a nice refresher. Oh. You're an eraser, right? Erase? Okay, now erase. Do erasing. There we go. It erased. Good. I like that. So our goal for today is going to be to add vectors. And so you can kind of see I'm talking about that here. Turns out it's basically a three-step process if you want to add vectors together. What do I mean by add vectors? Well, you could say that we added vectors when the airplane was going this way and the wind was going this way. That was, in a sense, adding two vectors. They happen to be the x and y component of this. But you can extend this to add vectors that are pointing all kinds of ways. So you can take a vector that's pointing that way and a vector that's pointing that way, and you can add those together. You can take a vector that's pointing that way and a vector that's pointing that way, and you can add those together. So that's what we're up to today. We're adding basically two, want to say random, but sort of like two random vectors together. And how do you add two random vectors together? Well, example 3 will be our first example, but let me just kind of go over the process. What you'll do is you'll take the vectors, you'll break them into their components. You'll then add the components, and then you'll take the components and go back into an r and theta. So notice steps 1 and 3 we've been doing yesterday, right? Take a vector, break it into its components. We did that yesterday. Take components and resolve into an r and theta. We did that yesterday. And just to sort of make sure we're all on the same page here, the first 2 examples are just reminding us of this. So example 1, how do you break vectors into x and y components? Well, here's a perfect example. Biff has a velocity. Biff's just humming along at 120 miles an hour. I hope that's not in a car. Anyway, he's going a direction 25 degrees east of north. Interesting direction. Sketch this vector and then do some other stuff. Okay, so first I want to sketch the vector. 120 miles an hour is telling you how long the arrow should be, right? So if you were drawing these with a rulers, you'd actually measure out 12 centimeters or whatever you would do. But you want to make sure you get the direction right. The direction is 25 degrees east of north. Well, which way is east of north? Well, I guess what I'll do is I'll draw like a XY axis here. So that would be east, this would be north, this would be west, this would be south. And he's going not east, not north, he's going east of north, which means, okay, think of it this way, not north, but east of north. How far east of north? 25 degrees. This is the 25-degree angle. See that? That's Biff. 25 degrees east of north. Means you face the north and then you rotate your head towards the east. 25 degrees east of north. So that's his direction, and his magnitude is be 120, so you just, like the length of the arrow is 120. Okay, there, we did that part. We sketched the vector. Then, solve for the x and y components of his velocity. Remember, the x component is you drop a plumb bob to the x-axis, and that's that shadow that you get on the x-axis. That is going to be the x component. And then you could draw the y component here if you want, or you can draw it over here if you want. It doesn't particularly matter. They're the same vector because they're pointing the same way and they have the same length. So even though they look like they're in different spots, they're actually the same vector. His y component is that. So maybe I'll just draw one y component. Will be enough on this diagram. So that's going to be his y component right there. So it's kind of like it makes a little rectangle, see? So it's like his velocity of 120 miles an hour in that direction. You sort of make it into a rectangle, and then there's your x and y components on the size of the rectangle. Okay, so I sketched the vector, and now I've sketched the components as well. I want to solve for these components. I'm going to grab those formulas. See right up there? You see that one? I'm going to grab it. It says that the x component is r cosine theta asterisk. Why do we have that asterisk there? I'll tell you why we have that asterisk there. The r is the length of the arrow. Yep, that's 120. The theta is not 25 degrees. No, it's not 25 degrees. Not. It's not 25 degrees. That's what the asterisk is trying to remind us here. Theta in standard position. Or maybe I should say theta as measured in. As measured in. That's the first asterisk, the single asterisk. Theta as measured in standard position. And remember, standard position is measured from the east, going counterclockwise. That's the theta you want to use. Okay, so keep this in mind. This formula assumes that theta is being measured in standard position. It's being measured from the x-axis, rotating counterclockwise. If you rotate the other way, you'd call it a negative angle. Let's not do that. So we're actually, it's not, let's see, so what is theta then? Theta is, well, if we went all the way north, it would be 90 degrees, but come back 25, right? 80, 70, what is that, 65 degrees? Yeah, 65 degrees. That's what you want to use here. Now I can press buttons. 120 cosine of 65 is, it's just about, yeah, I'll call it 50.7 miles per hour to the east. And then the y component, the formula is very similar, except it's got a sine, not a cosine. But you still want to use that theta in standard position. So it's going to be 120 sine of 65 degrees. So 120 sine 65, boom, we got like 108.8 or so is our y component. Okay. Now once you've done this a few times, you can get extremely fast. It's a matter of just grabbing these formulas, right? Just grab the formulas. Hey, our cosine theta. Hey, our sine theta. Just make sure you use the right theta is the big thing. Don't just grab an angle that somebody wrote. Just because I wrote 25 doesn't mean that's what goes into the formula, right? The formula is asking you for standard position. You have to make sure you put in standard position. Point made? Okay, cool. So that was an example of, let's change colors here. That was an example of breaking them into x and y components. Now let's do an example of resolving into r and theta. Again, this is review because we kind of did some of this for homework last time, but it's worth a review. So Bonnie's vector has an x component of -40 and a y component of -20. Sketch these components and do more stuff. Okay, you don't have to read the whole problem at once, you know, you can just start. I often just start. So it says Bonnie's vector has an x component of -40. So that's my east-west axis and stuff, right? So -40 means the x component means it's lined up right on the x-axis, right? That's what an x component does. It lines up right on the x-axis. -40 means it's pointing in the negative x direction. So it's west, kind of. So the x component is -40. What's the y component? You know what? Now that I see what my y component is. Oh, look what you did. Now that I see what my y component is, I see that I'm going to want to draw my x component a little bit bigger. So I'm going to go like this. That's 40. There we go. That's 40. So my x component's -40. Y component is -20. So see, this arrow should only be about half as long as that one. It's very helpful if you draw these things to scale. So it's -40. The y component is -20, so the arrow is half as long. It's -20 means it goes in the negative y direction, means it goes down or it goes south. Sketch these components. I did! Okay, draw the resultant. Okay, well, quick look back up here. Remember when we had the vector and we broke it in to components by making this little rectangle thing? Well, we're going to do the opposite of that this time. The -20 and the -40 are the sides of my rectangle. So here's your resultant this way. Right? So your resultant always forms a diagonal across the middle of your rectangle. They all vectors start at the origin, by the way. So you know, don't draw it this way is what I'm trying to say. So your resultant goes from the origin to this corner of the box. That's your, well, you could call it capital R with an arrow over it, just to give that arrow a name. That's your resultant. Now, solve for the magnitude and direction of the vector is basically saying solve for the r and solve for the theta. And again, theta is something you measure in standard position. So that's the theta measured from the x-axis. That's the theta. That's the true speed. That's the direction. So you can do this either by saying, hey, I'm going to do Pythagorean theorem now, or what amounts to the same thing. You can come back up here and say, well, there's my formula for r. Let me grab that. So r is equal to, you take the x component, you square it, you take the y component, you square it. Now you might remember from last time, I was saying when you're plugging into this formula, right, the negatives are not needed. Just, this is faster. Why aren't they needed? Because you're going to square the darn things, right? If I take a -40 and square it, it's the same thing as if I took a +40 and square it, right? So just don't even hit the button. Don't waste your time hitting extra buttons. And besides, if, as you recall from the last lecture, that's actually very dangerous because your calculator thinks that this is a negative thing. And it's not supposed to be. So if you use your calculator and you want to put in a -40, you have to put it in parentheses. And then it'll give you the correct answer, which is +1600. 99 times out of 100, when somebody messes up this formula, it's because they used a negative here, and or maybe even a negative here, and the calculator thought they were actually negatives and didn't square them, didn't get rid of the negative when it squared it, and so everything was all screwed up. So it's safer if you, it's safer if you just just don't bother with it. That's only true for this particular formula. It's only true for this formula because it's only true because we're squaring here, right? Anyway, with that all said and done, done and said. With that, I get out my calculator and do this thing. So I got a square root of 40 squared plus 20 squared. Whoops, plus I said 20 squared. Boom. It says 20 root 5. I hit the SD button, and we're getting R. We're getting R is about 44. Come on, you. 44 point. I'll call it 7. 44.7. I guess this is all miles per hour, right? What is going on with this thing? Okay, so that's 44.7 miles per hour. That's the true speed that Bonnie is going. She's got an x component of 40. She's got a y component of 20. But this vector here has a length of 44. Which way is it going? Well, the formula up above, you can probably see it if you get your paper in front of you. You do a shift tangent of the y over the x, always the y over the x. The signs are critically important here. So the y component is a negative 20 and the x component is a negative 40. So actually, I guess in this case, the negatives are going to cancel, right? So, but anyway, shift tangent of basically 0.5. So the angle that the calculator says is 26.6 degrees. And then this is the part where you say, wait a minute, that's not 26.6 degrees. What's the calculator talking about? And that, as you may recall, is the reason for the double asterisk. Double asterisk. So sometimes you have to add 180 to fix the calculator's result. Hopefully you remember this happening last time in some of our homework problems and so on. Sometimes the calculator gives you the right answer and sometimes it gives you exactly the wrong answer. This is exactly the wrong answer. It's kind of telling you this. It's saying, oh, 26 degrees, right? 26.6 degrees. Well, that's not the way it's going. It's going exactly the other way, hence the add 180, pull a 180. So add 180, exclamation point, and so the angle is really, what does that be, 206.6 degrees? Theta is 206.6 degree angle. Now in the, yeah, that's good, that's good. There we go. Okay, so we've done an example going each way, right? We've done first break them into x and y components, resolving back into r and theta. So this is the only part we haven't done, and because we haven't added vectors yet, we've had just one vector. This was just one vector with two components. This was just one vector. Now we come to the actual star problem of the whole show here today. This will be fun. Yeah, let's do this one. Let's stay with purple. Rover the dog is running 8 miles an hour at a certain angle, but he's on a ship that's going at a certain angle and a certain speed. So the dog is on a boat. The dog's going one way, the boat's going the other way. And if you were a stationary, what do they call them? Not hovercrafts. What the heck do they call those things? Drones. If you were a stationary drone looking down, which way would Rover appear to be going is the question. Now this might make a little more sense if we first just draw what's happening. So I'm going to first kind of draw like a north, south, east, west kind of thing, or I guess that's standard position, so that's 0 degrees and so on. Rover's going 8 miles an hour, the boat's going 13. So Rover's going to be a little shorter than the boat, just keeping that in mind. Rover goes at 105 degree angle. Where's 105? Well, remember, we rotate from here to here, that's 90. So you'd have to go another 15 degrees. So Rover's going that way. He's at 8 miles an hour, 105 degrees. Remember that notation? Nifty notation. It says the length of the arrow is 8 and the theta in standard position is 105. That's the dog. The boat goes 13 at a different angle. It's going 13 at 70 degrees. Okay, so 70 degrees would be like over here someplace. Now the boat's going 13, so it's a little bit longer than Rover. So something like this. Right, so there's the boat. going 13 miles an hour at an angle of 70 degrees. Now actually I'm going to cut this, kind of get it out of the way. I love that feature. Hey, what'd you do? Okay, now I love that feature. Yeah, now I love it. Okay, so that's Rover. Which one's Rover? I'm going to label this. This is Rover. That's the Rover vector, if you will. And then this is the boat vector, or the ship vector, going this way. Okay, fine. Draw these vectors. I did. Now sketch the resultant. Okay, this is cool. We haven't seen this yet. Sketch the resultant of these two vectors. Well, thinking back, well, just to example 2 here, when we had these two vectors, the resultant was, well, you drew like a rectangle, right? You're not going to be able to draw a rectangle here. But what you do draw is sort of the next best thing. You draw a parallelogram, and you try to do it real well. Try to draw it accurately. So you want to take this vector and sort of slide it up to here so it's parallel. This is easy to do if you have a drawing board with a T-square, but we don't. And then you take this vector and you sort of slide it up to there, right? So you make what's called a parallelogram. And now I can draw the resultant. And I usually use a nice red for resultants. And I'm trying to draw it accurately. Of course, I'm a little bit limited by the accuracy of my drawing. Like how accurate did I get the lengths of 8 and 13? How accurate did I get those angles? I don't know. It might be, for all I know, that this vector is a little bit, really points this way or something. I don't know. But that gives you an idea. The resultant is something like that. In fact, maybe I'll use the old capital R trick to say that's my resultant vector. Now, we want to solve for Rover's true speed and direction. That is what this resultant represents. Rover's running this way, but there's drift, so to speak. So which way does he really end up going? Well, if you're in a stationary drone looking down, you're going to see him going this way. He'll be aiming, his head will be pointed this way, but he'll be actually moving this way wise. So what are we going to do? What we're going to do is we're going to first, I like to organize this in a table. Maybe I'll erase that. Just make a little mini axis there. In fact, you know what? Well, yeah, I'm going to erase that too. I don't need such a big XY axis here. There's my XY axis. See, I need some room here. Okay. So, where are we? We got basically 3 vectors involved here. We have a rover vector. We have a boat or ship vector. And we have the true speed and direction, which I'll call the resultant, right? Now let's have 2 more columns here. In this column, I'm going to put the polar forms of the vectors. So the polar form of Rover is 8 at a 105 degree angle. And the polar form of the boat is 13 at a 70 degree angle. And this is what we would love to know, his true speed and direction. R would be the true speed, theta would be the true direction. Those are the 2 things we would really like to know. Now, you can't add 8 and 13, and you can't really add these 2 angles either. So what you want to do is you want to first convert these over to rectangular form. In other words, x and y components. You may remember a table like this from from last lecture actually. So how do you get, I want to put the x component and the y component over here, right? How do I get the x and the y component? Well, grab your formulas from up above. X component is r cosine theta. And my thetas are in standard position. Woohoo! So I'm ready to go. So all I got to do is go 8 times the cosine of 105. And I'm not going to push my buttons yet. I'm just going to write it that way. That's my x component. It would be r cosine of its theta, 8 cosine of the 105. And the y component would be the 8 times the sine of the 105. Beautiful. Now the boat, same thing. Take its r times the cosine of its theta. Take its r times the sine of its... That's not a sine. That's not a sine. I want a sine. 13 sine of 70. Okay. Now I'm going to punch buttons because here's the big thing. This is our great moment. You can add this and this together to get the total x component. And you can add this and this together to get the total y component. Again, we saw that in the last lecture. The x components add perfectly. The y components add perfectly. So that's why we're converting to rectangular form. Again, we cannot add r and r to get r. That doesn't work. But we can make x and y coordinates and then add the x and y coordinates. So now I'm getting out my calculator. Now I'm going to get out my calculator. And I'm actually going to type. So where am I? I'm right here. I'm going to actually type this in. I'm going to type, whoa, I'm going to hit the clear button. I'm going to hit type 8. I'm going to hit type. I'm going to type hit 8 cosine 105. Make sure you close the parentheses. You have to close the parentheses. Then I can say plus 13 cosine 70. Close the parentheses again. Hit equals. No, not that. Not that way. Okay, here we go. Use an actual pen. 2 point, and I like to carry some decimals here. 3, 7, 6. That's probably pretty good. 2.376. That's my total x component. By the way, I'm rounding. I'm not cutting off. If I cut off, it would say 2.375. But the next one's a 7, so that means a 5 has to round up to a 6, right? Make sure you do rounding, please. Meanwhile, I'm going to add up the y components. I hit 8, sine button, 105. Notice you have to close the parentheses. Plus 13, sine of 70, close parentheses, equals. And I'm getting a y component of, if I go 3 decimal places, 19.943. And so what that means is that this red R here, we just calculated, has an x component of 2.376, a very small x component, and it has a y component, that's the y component, right, of something kind of big, really, 19 point something, so that would be along the y-axis. Now, to get the true speed and direction means we want to come back and get the actual r and the theta. So now I'm going to grab out the old r equals, take the x component squared plus the y component squared. Remember the Pythag theorem? And you don't have to worry about negative. Actually, we don't have any negatives, never mind. So we're just going to go square root of, type in my 2.376 and square it, plus type in my 19.943 and square it, equals, and if I use maybe 2 decimal places now, 20. 3 sig figs is plenty for my final answer. 20.1. Rover's true speed is 20 miles an hour, believe it or not. That's because the 8 and the 13 are kind of lined up a little bit, right? If they were lined up perfectly, he'd be going 21 miles an hour. Boy, that's pretty close. Well, it is what it is. So he's going pretty darn fast, 20 miles an hour compared to the Earth. And his angle is, remember you do the old shift tangent of y over x, or I should say the x component over the y component. And let's see now here. Shift tangent of 19.943 over 2.376, close parentheses, equals, we're getting an answer of 83.2 degrees. And does it look like we need to add 180? No, I think that looks like 83 degrees. Yeah. I think we can believe the calculator this time. 83.2 degrees. So there we are. There's his true speed. There's his direction. Okay, so it's good to, after you get through a problem, it's good to sort of stop for a minute, look back on it, maybe just kind of chew on it a little bit and say, what just happened here? What just happened here? So I'm going to get out the yellow here. What happened was we had Rover, and we said, okay, Rover, I've got your r and theta in standard position. I'm going to put you into x and y form, get your x and y components. And then we said, oh, boat, you're a boat. And that's your r and theta. We're going to put you into rectangular form, x and y component. Because then I can add you guys together. Now, I know you guys are going to go that way because that's what the parallelogram tells me, right? You draw a parallelogram. That's actually called the parallelogram rule. I How do you like that? It's a rule. So you do the parallelogram. Anyway, once you've got the x and y components, you can add this way. These two things added up to that. These two things added up to that. So that gives you the x component and the y component of the resultant of the big red arrow, which you then use these two famous formulas to get back to your r and theta. So it's a very interesting process, I think. It's like you're kind of going in this big circle, right, to solve this problem. Okay. Okay, two more examples. The main reason for this next example is to it's a very similar example, so it's to consolidate the process a little better, but it adds the little twist at, look at these weird angles, 10 degrees west of south. Wait a minute, didn't we do that up here? Ah, see, we've seen this before. We've actually seen this before, east of north, north of west, whatever. So that's the only extra twist to it. So, which means you might as well just pause and try this one yourself. Try to make sure you're getting this. So you're pausing, right? You're gonna pause and do this yourself. Okay, cool. Welcome back. Scuppers sails 15 mphs at a certain direction. He's got a breeze that goes in a different direction. Sketch these two vectors, because the way he's going and the way the breeze is going are going to add up to be the way that he's, what are you doing? The way that he's really going. What is that now? I don't want to go, get, dumb thing. Okay. Let's see now here. What are the two? Looks like I need to give a wind speed. Yeah, I kind of forgot that. Sorry. Let's have a 50 miles an hour. Let's have a 20 mile an hour breeze. Good thing you watched the video. You'd be all confused, right? Yeah, typo. Let's make that a 20 mile an hour breeze, because the breeze has to have some kind of miles per hour to it. Otherwise, we can't add it to anything. Back to Scuppers. Scuppers is going 50 miles an hour, 10 degrees west of south. Which way is that? West of south. Well, the south would be this way, but he's not going south. He's going a little bit west of south. And it's only 10 degrees west of south. So this is where the 10-degree angle is. And his speed is 15. Okay, just call it a 15. Actually, what I think I'd like to do is write this in the polar form. So it's 15 at an angle of, and you want to put the standard position in. So you just got to remember that the standard position is measured that way, right? You start at the x-axis and you rotate counterclockwise. So if we know that this is 10, then can you tell me what that is? Well, that's 0, that's 90, that's 180. If you add 90 again, you get to 270. So you could say 270, take away 10. It's a 260-degree angle. So that's Scuppers. Scup for short. 50 miles an hour at a 260-degree angle. Okay, cool. Get this out of the way. What about this other thing? What's the other thing? It's a breeze. And it's 20 miles an hour. It's a little bit longer. 80 degrees west of north. West of north. Well, north is this way. So not north, but 80 degrees west of north. That's quite a ways west of north, right? So that's saying that this is an 80-degree angle west of north. And I'm trying to make the arrow a little bit longer than this one, because this one's a 15. This one's supposed to be like a 20. So maybe up to there. Now I'd like to write this vector in polar form as well. You have to use the theta in standard position. So again, you don't just go grabbing numbers that they print. Just because somebody printed an 80 here doesn't mean that that goes into the formula. Okay, you got to be careful. What we're going to want is we're going to want standard position. And standard position is measured this way. And so what is this theta? Well, it would be the 90 you get here plus the 80 more. You'd be 170. So let me write 170 degrees right here. And then this is the breeze. So you get scup and you get the breeze. Okay, cool. Back to our question. Scupper sails 15, heading 10. Got it. In a breeze that goes 20. Got it. 80 degrees west of north. Got it. Sketch these vectors. Did it. Now the resultant. Okay, that's where I get out my red pen. The resultant. So remember, the idea is to make a parallelogram. So this vector here, you would kind of want to slide, kind of like think of like sliding it up over to the other end. And then this vector here, you would kind of want to slide, whoops, make it look a little bit better. Slide over to like this end, like this. Okay, so that's the slide that you do. And then all vectors are starting at the origin. So you're coming across the middle like this. This is your resultant, which I will call capital R, with an arrow to say it's a vector. That's the resultant. So you can kind of see what's happening here. Scuppers has got his boat pointed this way, but there's a bit of a cross breeze, and so he's drifting this way as he goes. And so his actual speed and direction is that away, and it's actually quite fast, right, compared to a stationary hovercraft or drone. I keep saying hovercraft. Drone. It's just a drone. So what do we do here? Well, we can start making that table again. So we can say, okay, we've got Scup. He's a vector. We've got the breeze. That's a vector. And we've got the resultant. That's a vector. Make a table that has these rows and these columns. So there's the polar form and there's the rectangular form. So the polar form of Scuppers, that's again where you give the r and the theta, is 15 at an angle of 260 degrees. And the polar form of the breeze is 20 at an angle of 170. And we'd love this, but we can't get there from here. We have to go sideways, right? We have to go that away, then we'll go that away, then we'll go that away. Okay, so there's a bit of a loop you got to go here. So remember here, I'm just going to write this down. The x component is 15 cosine of 260, and the y component is 15 sine of 260. The x component is 20 cosine of 170. The y component is 20 sine of 270. So those formulas were up on page 1, but it's always going to be cosine for the x direction, sine for the y direction. It's alphabetical order, CS, XY. Then this is the part where you get out your calculator and start pushing buttons. So I take this plus this. I add my two x components together. Let's see, I type in 15 cosine 260, close that, plus 20 cosine 170, close parentheses, equals, bada boom, bada bing. And here's why it's nice to be using the standard form, is because it tells you automatically, by the way, you've got a negative. Did you know that? You have a negative x component. Now, if you look at this over here, you'll say, yeah, I reckon that this vector would, if I dropped a perpendicular, yeah, it would have an x component, wouldn't it? But that was negative. It would also have a negative y component, right? So you can kind of see that. So the y component should also come out negative. If you're using this, if you're using the standard position angles, the calculator will take care of that for you. So 15 sine of 260, add 20 sine of 270. What? 170. That's supposed to be a 170. 170. That's better. You end up with a negative 11.299. So it would also be a 30. What a coincidence. So 170, not 270. Okay, that's better. So now that's my x component. That's my y component. I can put them together using Pythag to get my little r, and I can use shift tangent y over x to get my theta. Now again, when I'm plugging into the first equation to get the little r, the magnitude, I don't enter the signs at all. I just go, okay, square root, take a 22.3 and square it, because that's the same as taking a negative 22.3 and squaring it. So why hit the negative? Doesn't matter. Plus 11.3 square that equals, and it's, boy, it's just about exactly 25. Who'd have thunk it? So it's just about, let me maybe notice my red here. It's just about 25. I'm going to put 25.0. I got 24.9996. So to 3 sig figs, that's 25.0. And then the theta, you do a shift tangent, put the y component, which is a negative 11.3, over the x component, which is a negative 22.3. The negatives are important here, except for the fact that they cancel in this particular case. But anyway, I'm getting an angle of, well, I'm getting an angle of 26.9 degrees. But remember, this is the formula that has the double asterisk on it. Sometimes you have to fix the calculator by adding 180. Does that look like we need to do that here? Well, I'd say so, because 26.9 degrees would be if over here, right? You always measure from the x-axis, coming this way. And that's not the way, my vector doesn't point that way. It points exactly the other way. So then I would go 180 plus that, and I would get 206.9 degrees. 206.9 degrees. So try to squeeze that in there. Now actually, if I want it to behave, I give them the answer in the same format that they gave us the question. They gave us the question using this kind of a format: a speed in miles an hour and a heading. So we should turn that into a heading then. So that's 206.9 degrees, huh? Well, headings are always from the north or south, so we want to actually try to figure out what this angle is. Heading so many degrees west of south. So how many degrees is that? Well, there's a couple of ways you could do it. One way you could do it is, you know, it's 270 to here. So you go 270 minus the 206.9. Maybe I'll just do it that way. 270 minus the 206.9 is giving me 63.1. 63.1 degrees west of south. There's a beautiful answer right there. Cool. Well, I hope you like this adding vectors stuff. It's fun. So now you can add forces, you can add velocities. This last example is forces. People are having a tug-of-war. You can actually figure out which way it's going to move. Which way you guys are going to move here. I put this example in to illustrate a couple things. First of all, we got 3 people: Vladimir, Olga, Mikhail. 3 people. We're going to add 3 vectors together. Now, to do that, usually there's other methods of adding vectors where you'd have to add 2 of them and then add the third, but we don't even have to do that because this method is perfect. I don't even have to draw a diagram. All I have to do is go like this. Vlad pulls 150 at a 45-degree angle. Nice of them to give it to us in standard position, ain't it? Olga, where's Olga? 90 at a 210-degree angle. Again, they're giving us standard form. That's making it even nicer. Mikhail is going 170 pounds due south. Okay, so they're going to make us think a little bit. So due south is this way. What's the theta in standard position? You might remember that's a 270-degree angle. So I don't even have to draw the vectors, really. I mean, I could, but it's almost like you're an accountant, right? You have your polar form, you convert to the rectangular form, and we'll get our resultant in a little bit here. So the rectangular form, I'm just going to write this out. In fact, when you get really good at this, you won't even write it out. You just get out your calculator right away. But the rectangular, you're going to have a 150 cosine 45 degrees x component. This is going to be a 90 cosine 210 degrees x component. This is going to be a 170 cosine 270 degrees x component. And so if I add up all those x components right now, 150 cosine of 45, close parentheses, plus 90 cosine 210, close parentheses, plus 170 cosine 270, close parentheses, equals. I'm getting a, whoa, hit the SD button on that one. I'm getting an x component of just about 28.124. I do like to carry some decimals when I'm still in the middle of my calculation. So apparently we have an x component of 28. Now the y components are all kind of the same thing, except you use sines instead of cosines, right? So this is going to be a 90 sine 210. This is going to be 170 cosine 270. Okay, and then I can add up those y components. So I type in 150 sine 45, close parentheses, plus 90 sine 210, close parentheses, plus 170 sine 270, close parentheses, equals, bada boom, bada boom, bada boom, boom, bing, bada boom, bada boom, bada boom, bing, bing, negative 108 point, I guess I'll go the same number of decimal places, 934. Okay, and then this is the part where you say r is the square root of 28.124 squared plus 108.934 squared. Again, I don't have to use the negatives because I'm just squaring the darn things. So I'm just going to type this stuff in, 28.124, that gets squared, plus 108.934, that gets squared, equals square root of answer. I kind of forgot to put that in the square root. Okay, here we go. To one decimal place, I got 112.5 for my magnitude. So the net force is going to be 112 pounds. Now to get the theta, I would have to go like this. Y over x, right? So you take the negative 108.934 over the positive 28.124. And this is telling me, let's see now here, shift, tangent, negative 108.934, divided that by a 28.124. My theta, my calculator is telling me negative 75.5 degrees. And I'm glad you made it to the end of this lecture because this is a very important point. If I didn't draw the vectors, how do I know whether I'm supposed to add 180 or not? Remember, we always, when you do the shift tangent, you always have that question. Do I have to add 180 to fix what the calculator says? Sometimes you do. Didn't we have to do that back here? We did. We had to do that back here, right? How did we know that we did? Because we said, well, the calculator is giving me this angle, but I can tell by looking at it that that's the wrong way. That's the wrong way. Well, with this one, I suppose you could try drawing the vectors, or you could take a shortcut. You don't have to draw all the vectors. Oh, for goodness sakes. Okay, you go. Look at resultant components. In other words, these numbers. We have an x component of 28, roughly, and a y component of like negative 109. Okay, when we added up the vectors, we said the resultant goes this way. It goes positive 28, negative 109. Well, that means that the resultant, remember you draw your rectangle, go through the middle of the rectangle like this. Does this look like negative 75.5 degrees is correct? It does. Now, if we had instead a negative x component of 28 and a positive y component of 109, then we'd say, no, it's not 70, it's not negative 75. You'd have to add the 180 to it. So notice that you'd be doing the same shift tangent. Y over x would be 109 over 28 negative. Whereas here it's 109 over 28 negative, right? So just like take this and draw it, and then you'll know which quadrant you're pointing into. We should be pointing into this quadrant. This is the fourth quadrant. 1, 2, 3. This is the fourth quadrant. And the angle they're giving us is in the fourth quadrant. We're fine. That's the actual angle. It's negative 75.5 degrees. And so here's our true speed, or not speed, I guess it's a force, our net force. Our net force is somehow this will weigh 112.5 pounds. Now, if you want to have some fun, what I would do is I would get out like a protractor, ruler, and I would try to draw these all to scale. Draw Vladimir and Olga to scale. Draw Mikhail to scale, and then try to convince yourself that those three really do add up to something like this. Something at that angle, something about that length. Okay, that's a pretty good lecture for adding vectors. I like that. So next time we're going to start getting into some actual AC electricity, which is what this is all for. This is why we're doing vectors, is to look at AC electricity. But for now, we'll just add some dogs and stuff. End.